Alright, so we'll try to finish most of the rest of this section in one video, I hope. Uh, Sorry about that. I had to stop the video for a second. Um, One side note is we were just talking about that local extreme value theorem that said that it has a local maximum or minimum. If the derivative of f at c exists, then the derivative of f at c is equal to 0. Um, the opposite of that, the converse of that, isn't necessarily true. We can have a derivative at c equal to 0 and not have any local extrema there. And the figure 4.9a is an example of that. There's no local max or minimum here, but you'll notice that with this, what is probably somewhat what transpired, transposed um, cubic function, that there's no maximum or minimum, but we definitely have a slope here that's equal to 0, right? Right here, you can see that. All right. So if you consider something like f of x equals x cubed, we know that that looks something like this, right? And we know that the derivative of that, if I take the derivative of it, is equal to 3x squared, right? So don't get caught up in your whole derivative thing from the last chapter. So if I wanted to find at 0, f prime at 0 is equal to 0, but you'll notice that at 0 here, I definitely don't have a maximum or minimum, right? What I have, if I were to zoom in really, really close, would be something where it actually goes through and comes right through here really quick and then goes back up. Okay, and so right there at 0, I would have a slope of 0. I tried to get a different color there. All right, so my tangent right there at 0 would have a slope of 0, but I don't have a maximum or a minimum. That's what I was getting at there. Alrighty. This is actually what we call an inflection point. And you'll start seeing that term thrown around a little more, and we'll talk more about it. All right, but it's not a max or a min. Okay. All right. Let's see what else we have. Similarly here on this graph, this looks like maybe a cubic or a cube root type function. We have the slope f prime of c does not exist because we have a vertical line, right? That's why. But you can see, again, there's no local maximum or minimum at c. So that local extreme value theorem, it works one direction. If there's a local max or min, then the derivative of f at that value is equal to 0. It doesn't mean that when the derivative is equal to 0 that you're always going to have a local max or min. Alrighty? Okay, so let's take a look at an example here. On the next slide, we have here y is equal to x squared natural log of x. So if we look at the derivative of this, dy dx is equal to, and here we're going to have to use the product rule, right? So 2x natural log of x. Right here, I'll put those in. Plus x squared times 1 over x. That's the derivative of the natural log. So this was my dx of x squared And this was my dx of natural log of x. I just used the product rule there. All right, so this means that we have 2x natural log of x is equal to x, or I'm sorry, is equal to plus x, right? If we wanted to, we could factor out an x, and we could say that dy dx is equal to x times 2 the natural log of x plus 1. Okay, so if I look at that, then I could try to find my critical point, right? Where, remember, my critical points are where either my derivative is 0 or it fails to exist. So if I look at where my derivative is 0, then I have x times 2 natural log of x plus 1 is equal to 0. So that means x equals 0, or I can also look at 2 natural log of x plus 1 equals 0. This first one, that one's not true because it's not in my domain, right? So if I look here, my interval is from 0 and up, right? Because I can't take the natural log. If I look at my domain here, it's from 0 to infinity, okay? So this isn't in my domain. So I'm going to ignore that. If I look at my second one, what I end up with is the natural log of x is equal to negative 1/2 if I solve, right? So then if I take both sides to the e, then I have e of natural log of x is equal to e to the negative 1/2. So that this over here becomes x equals e to the negative 1/2. All right. Which is the same as 1 over square root of e. So that's where you see this. So what we have is a local and absolute minimum here at e to the negative 1/2. And then if we were to substitute back into the original equation, we would get our what our y value f of e to the negative 1/2 is. Alrighty? So that's how we can find a local extrema here. Okay, keep an eye on those domains because sometimes they'll come back to bite you. And it's really easy to suddenly say, oh, x equals 0 looks like a great spot for a minimum. So the procedure for locating absolute extreme values on a closed interval, assume the function is continuous on the closed interval AB. Locate the critical points C and AB where the derivative of f at C is 0 or it does not exist. These points are candidates, just candidates, for the absolute maximum and minimum. Evaluate f at the critical points and at the end points AB. Don't forget this step. It's really easy to spend all your time in the middle of the function on the interval and then forget to look at the end points. Okay. Choose the largest and smallest values of f from step 2 for the absolute maximum and minimum values respectively. So if we take a look at in our next picture here, we're going to use here f of x is equal to x to the 4th minus 2x cubed on negative 2, 2. So we can see this is continuous, and it also is on a closed interval. So we know by the extreme value theorem that there's going to be an absolute maximum and a minimum on this interval, right? So let's go ahead and take the derivative, and we're going to get the derivative of f is equal to 4x cubed minus 6x squared. right? So if I want to write that just a little bit nicer for what I want to do here, 2x squared times 2x minus 3, and that'll do that. Okay. So if I want to evaluate what that looks like as when it's equal to 0, when that derivative is 0, then I'm going to say f prime of x equal to 2x squared times the quantity 2x minus 3 is equal to 0, which means I want to look at when 2x squared equals 0 and when 2x minus 3 equals 0. So I want to look at when x equals 0 and when x equals 3 halves. So my candidates then for my extrema are going to be at x equals 0, at x equals 3 halves, at x equals -2, and at x equals 2, because those are my endpoints, right? These two are. So I'm looking at where I have zeros on my slopes for my tangents, then that's from the derivative, and I'm looking at my endpoints. So if I look at this, f of -2 is equal to 32. If I look at f of 2, that's equal to 0. If I look at f of 3 halves, that's equal to -27/16. And if I look at f of 0, that's also equal to 0. Okay, so what I find is that I have an absolute max that you can see here at -232, and then I have an absolute and local minimum at 3 halves and -27/16. I have no extrema at 0, 0. Okay, this is not a max Orman. Okay, so one of those inflection points that I was telling you that about. And then I don't claim that I don't have a local max, remember, at 2 because it's the endpoint. Okay, and so we're not claiming local minimums or maximums at any of the endpoints. Alrighty? Okay, so one more page. Here we're going to look at the function f of x is equal to x to the 2/3 times the quantity 2 minus x on -1, 2. So again, by the extreme value theorem, there is an absolute maximum or minimum because this is continuous and the interval is closed, right? So if I look at the derivative of this, let me write it over here. I have the derivative of f is equal to, and I'm going to use that chain rule, 2/3, hold on, that's really ugly, is equal to 2/3 x to the -1/3 times 2 minus x plus x to the 2/3 times -1, right? So if I put this together a little bit nicer, what I'll get is, let's see, 2 times 2 minus x all over 3 times x to the 1/3 plus, well, it's actually going to be a minus x to the 2/3. So I can get, see if I multiply the last term by 1/3, and I have 4 minus 2x minus x all over, make it minus 3x there. So I'm going to multiply that last term. We're multiplying this last term by, let me move this over. X to the 1/3. That was to the 2/3. And so I'm multiplying it by 3x to the 1/3 over 3x to the 1/3 so that I can get a common denominator there. So I'm going to end up with 3x on the top, and all of this is going to be over 3x to the 1/3. And so I'm going to get 4 minus 5x all over 3x to the 1/3. So if I want to find my critical point, right, I'm going to set f of x equal to 0. So I'm going to have 4 minus 5x over 3x to the 1/3 is equal to 0. So I'll have 4 minus 5x is equal to 0. So x equals 4/5. Notice I can also look at where this denominator, because then I'm not going to exist. So when 3x to the 1/3 equals 0 is another critical point. So x equal to 0 is another candidate. So if I look at the candidates here, I have x equal to -1. That's our starting point. X equal to 0, x equal to 4/5, and x equal to 2, right? And so if I look at those, what I find is f of -1 is equal to 3, and you'll notice that's an absolute max there. F of 0 equals 0. If I look at f of 4/5, I'm at 1.03, and f of 2 is equal to 0. So here you can see how we have an absolute max at -1, 3. We have a local max at the 4/5, 1.03. We have an absolute min at both 2, 0 and at 0, 0. We also have a local min at 0, 0. We don't have a local min at those endpoints, at the endpoint, because we don't use those. Okay? So that basically gives us our candidates, and it allows us to find our absolute maxes and absolute mins. Okay? Let me know if you have any questions. Sorry, it took 3 videos to get through this, but I hope it's helpful. I'll be seeing you soon. Bye-bye.